Okay, well, thank you very much for that very nice introduction. It's actually quite a rare mineral, but it does exist. So thank you once again. It's a real pleasure to be here to tell you about our work, and I'm especially pleased to be a part of this series on matter under pressure. I've taken a look at a number of the previous lectures in this series, and I hope what I talk about today is complementary to that. I focus on high pressures, but also, as was mentioned, high pressures as they relate to materials, to chemistry, to high technology ultimately. So that's somewhat different perhaps than some of the pressure studies that you've heard about in previous talks. The outline of my talk is shown here. I'm going to start with the high pressure context, more about how our work fits into this bigger picture of pressure. Then move on to a discussion of hydrogen and hydrogen-rich materials. This is really the starting point for so much science that's quite exciting. And then give some examples. First, the binary superhydrides, as I call them, moving on to what I'll call a tale of two ternary systems, some related findings in other materials that I think are quite interesting. Some are quite recent results. And then a few words on the outlook. So the themes I'd like to weave through this talk are listed here. As has been discussed in previous lectures, there's really a very strong synergy between theory and experiment in my area of matter under pressure. And this is quite a new development, but one that's very, very important and has made enormous progress for us over the last few years. Also, I want to stress the multiplicity of techniques that we must use. We don't have the luxury of studying materials under ambient conditions, all the beautiful kinds of microscopies and electron-based probes that you have for studying materials, condensed matter at high pressure. So we have to be especially careful and clever in using different techniques to really understand what's happening in our materials. And that means a need for careful assessments of results, and sometimes these careful assessments are not quite what they should be, and that's led to a few controversies in our field over the years, and I'll maybe touch on some of those. There's an emerging consensus, despite some of the controversies you may be aware of, but there are continuing questions both on the technological relevance and ultimate deployment of the materials, but also continuing questions that are quite important fundamentally, and there are new challenges for both experiment and for theory. So let's start with this slide. Pressure is a remarkable thermodynamic variable. It spans some 60 orders of magnitude in the visible universe, the kinds of pressures one has in intergalactic space to what you have inside, say, the center of a neutron star. The range of interest to us is over here. It's a subset, but still quite a wide range, and this is the range of conditions over which materials transform. We have chemistry. It's also the range of conditions that's relevant to planetary interiors as opposed to stellar interiors where you have fusion processes. And so there's quite a lot of very interesting applied interest in studies of pressure effects on materials for planets, high technology and chemistry. Here's a table to convert among different pressure units that we use in our field, and I'll be using different ones as we go along. So I also would like to start with how this work maybe fits in with some of the previous talks. This is from a recent National Academy of Sciences report on high energy density science, and it shows here on the x-axis pressure, and down here energy density, and since energy is just pressure divided by volume, this is joules per cubic meter, which is equal to a Pascal, and this is a log scale. But it shows the range of conditions of interest here, and then temperature also on a log scale. Starting in a more familiar regime here, here's ambient, all the way up to fusion processes and the kinds of really exotic phenomena that occur in many astrophysical objects. This is the range of interest that I'll be talking about here, what we call cold matter on this scale. And at higher pressures or higher energy densities, quantum matter. And this is actually a relatively new field. Cold, dense matter has a lot of quite intriguing properties, distinct from what you have at much higher temperatures, which I'll come to. So it's a very exciting area. It's also exciting because, as is the case in many fields, a lot of the great discoveries are really occurring at the borderline between these different disciplines. So it's a very rich area of study taken as a whole. So let's start at the beginning here of chemistry in the sense of supernova collapse and nucleosynthesis. And this gives rise to the cosmic distribution of the elements shown here. And these are some of the principal elements I'll be talking about, in particular hydrogen. But from these exploding bodies, we have, of course, the periodic table as we know it, Mendeleev's table. And then we have hydrogen here. And so part of what I'll be discussing is what happens when you take these elements that are formed under extreme environments and then you recompress or recombine them in interesting ways to make interesting materials and see interesting phenomena. So let's start with hydrogen. Why should hydrogen be so important? Well, not only is it the most abundant element, it's really where so much of our modern physics begins in terms of the development of the chemical bond due to Heitler and London and Pauling during the early years of quantum mechanics. We have also, during the early years of quantum mechanics, the idea that if you compress it enough, you could form a monatomic metal, the famous prediction by Wigner and Huntington. It's abundant in the cosmos and therefore in large gaseous planets, not only those in our solar system, but in the thousands of solar systems that we've now discovered outside our own. These bodies contain a vast amount of hydrogen, as well as, of course, the hydrogen in stellar interiors. Moving on to its fundamental importance, when you think about hydrogen as an electron and a proton, and you think about it as a many body system, it's got a beautifully symmetric Hamiltonian here, but it's also something we need to consider in a many body sense. So a lot of exciting work has gone into trying to understand many body theory in dense systems in terms of just the one proton and one electron system. And part of the issue is that hydrogen, at least the first isotope, the proton with an electron, has a very large zero-point motion because it's the lightest nucleus. And so you have to consider its zero-point motion. I like to call this really the element of uncertainty, which plagues a lot of the theoretical calculations and approaches that I'll come to. And then finally, in the much more extreme regime, we have the path to fusion ignition, at least for the DT isotopes. And this is a great success, of course, of modern science. This has now been repeated numerous times. Fusion ignition with yield at the National Ignition Facility at Lawrence Livermore Laboratory. So great excitement and very important for this whole picture of why hydrogen is an important element. So let's go back now, though, before discussing some of the quantum mechanics, and think about what happens when we compress atoms, and think about this maybe the way people did 100 years ago. What happens when you compress atoms? Well, the conventional view was you have spheres that compact, and we, in the early days, considered them as a first approximation as hard spheres, like cannonballs that stack in this nice symmetric structure. But this presented a problem for how we could understand in the 20s, for example, the very high densities of astrophysical objects. The atoms must take on some other form. They must perhaps be disrupted in some fashion, and this is a problem that Fowler and Bridgman addressed in a couple of papers. At some high density, in this little model here, we have just one electron and an orbit around an atom. with increasing compression, you have a stripping of the electrons from the nuclei, and you go into some kind of a tenorate plasma, or in some cases, a metallic state. Well, why does this occur? This occurs because if we appeal to basic density functional theory, or ideas that go back to Thomas, Fermi, and Dirac, we have the rise in the kinetic energy of the electrons, and this rising kinetic of the energy of the electrons causes this dissociation of the atoms into this dense plasma state. And this has implications, of course, for chemistry as well, because it also means that when you compress molecules, well, here take the very simplest molecular system, a system of molecules in a solid, the electrons are no longer going to be stable in the bonds, and they must also redistribute and ultimately give you some kind of dense atomic, monatomic solid, as was suggested by Wigner and Huntington. And this also gave rise to a conjecture also, again, from the mid-20s, this conjecture, which is the first footnote in this famous paper by Wigner and Huntington, that the ultimate state of molecules would be some kind of metal, everything will become a metal, or some kind of valence lattice at some high pressure. That is before you reach a regime of nuclear processes. But in terms of condensed matter, that would be the ultimate state. And it wasn't until just about a decade or two ago that we realized this is not quite true, and a lot of very interesting things happen along the way. This would simply mean that chemistry is over by the time you get to those states, but in fact, there's a rich chemistry that persists to much, much higher conditions, and that's something that I want to touch on numerous times tonight. So another important point I want to make is, if you just take a simple system, and an example of this interesting chemistry, you take a textbook free electron metal like lithium or sodium. Here we have this nice BCC structure. It's a nice shiny metal. It's what we built our modern theory of metals in terms of quantum mechanics on. And if you compress it to, say, a megabar of pressure, 100 GPa, something quite dramatic happens. The electrons don't stay in the conduction band. They don't do what I showed in that simple model. They actually take on some very different character, and they condense into pockets and other places in the structure. In fact, in some of these elements, simple elements, you actually can turn this metal into an insulator. So it's the reverse of this dogma or paradigm that we had for, say, a century. What this means is, if you think about the periodic table, the elements and then the elements in combination, we really have a whole new regime of chemistry to deal with when we're talking about these very high compressions. And in a way, we need a new paradigm, and the conventional Mendeleev table really doesn't work at the level of being a predictive tool like it is at ambient conditions for the kinds of environments we're talking about here, and what I'll talk about in the case of the emergent phenomena I'll describe, which is mainly superconductivity. We have altogether new structures, bonding, and properties across the elements and compounds, and there are really profound implications for creating new materials, and actually, I would argue, for discovering new physical phenomena that simply we don't observe or have a handle on under normal ambient conditions of pressure. Another key point that I want to highlight is the enormous free energy that accompanies the compression of materials now over this range of conditions that we can make or accomplish in the laboratory. So you just take this simple salt, cesium iodide, and you compress it, say, to 300 gigapascals, 3 megabars, and then you integrate that curve, VDP, to get the free energy work. You see that the work is on the order of 10 electron volts, and many systems is beyond that. So really, pressure volume work, or the free energy, can exceed bond strength. So obviously, very different chemistry is happening because you're exceeding the strengths of known chemical bonds. What this also means is we have to think about two kinds of stability. We have thermodynamic stability that's sort of implied by this. We're looking for the ground state of a material at very high pressure. But we also have the possibility of metastable states, so kinetic stability, that could be very important. And after all, there are a lot of interesting materials that are kinetically stable. Diamond, for example, is kinetically stable. It's not thermodynamically stable under ambient conditions. And it's very useful, of course, as a stone, as an object, as a consumer gem, but it's extremely important for many kinds of advanced technology. So what this means is that pressure is a knob for tuning across energy landscapes. I'll come back to this several times, looking for minima, both the metastable minima and global minima on the system. So what I'd like to do today is really focus on one kind of emergent phenomena that occurs, and that is the very important one of superconductivity. Of course, this was discovered by Camerlingh-Onnes serendipitously back in 1911 when he cooled mercury, of course, at ambient pressure, and found it lost resistance at about 4.2 Kelvin. And ever since that finding, people have dreamed of whether or not one could use this to revolutionize a variety of technologies. Of course, low temperature superconductivity is used in technologies, but if we had this at much higher temperatures, it could revolutionize areas such as the electrical grid, transportation, computing and electronics, and advance various kinds of probes for medicine. So it's a dream we've had for many, many years. Now, I also would like to point out before starting that there were two important contemporaneous inventions that I want to talk about that will weave through what I'll describe, and that is the rollout of the first complete theory of superconductivity due to Bardeen, Cooper, and Schrieffer. And within a few months of that, the rollout of the first paper of describing this device called the diamond anvil cell, this from the National Bureau of Standards, then located in Washington, D.C. So it's curious that within a few months, both of these papers were published. So just one slide on sort of the essential features of superconductivity that I'll be discussing and are important for our story. First of all, for BCS superconductivity or conventional superconductivity, we have this idea that they're Cooper pairs of electrons coupling with lattice distortions that give you superconductivity. There are various approximations you can make to approximate the critical temperature where you'll have superconductivity. And sort of three key ingredients in this theory are the high phonon frequencies, large electron phonon coupling, and what's known as a high density of states at the Fermi level, which means you have a lot of electrons right at the top of the conduction band that are available to pair up and make Cooper pairs. Now, various extensions have been are very important to this. One is the concept of the Meissner effect, where you can quench superconductivity with a magnetic field. This is an important test of superconductivity. And for certain types, type 2 superconductors, you can see the vortices in the structure. And so one of the goals of some of our work is to look for these in these systems. So for the diamond cell, I mentioned it was basically discovered or rolled out, invented in the mid-1950s, but over the years it's undergone significant changes, and quite a wide variety of tools are used based on this, and they're all based on diamond because diamond has very high strength. It's also a wonderful window through which you can probe your samples, and a variety of them are shown here. I actually brought two of them with me. One of them is like that first one. This is a diamond anvil cell with two diamonds, and it contains a superhydride, a superconductor at 100 GPa. So this is a million atmospheres of pressure on this superconductor I'm holding in my hand. And here's a much smaller one, like that one of those on the top. This is a very small one. We call it a pencil cell. This also has two diamonds, and this sits inside a very large magnet for doing Meissner effect measurements. And this can also reach pressures of 100 GPa, 200 GPa. So these are small devices, but very, very powerful and very useful. We can bring lasers in to synthesize materials. We can build coils or circuits into the diamonds for measuring transport properties and magnetic properties. We can put coils around the diamonds or put them inside the sample to measure magnetic properties, for example, the Meissner effect. We also couple all this with very large facilities, so it's a combination of very small scale science, very small samples with very large facilities, and these are some that we use. For example, the Advanced Photon Source, which is near me in Chicago, where we use this for X-ray diffraction and spectroscopy. We also use, and we've been using for some 40 years, the National Synchrotron Light Source, or National Synchrotron Light Source 2 at Brookhaven. Infrared spectroscopy is primarily used there. We use the spallation neutron source for characterizing the hydrogen sublattices at Oak Ridge. The National High Magnetic Field Laboratory is very important for these Meissner effect studies. And we also use from time to time the National Ignition Facility, which is the site, of course, for where ICF ignition was and continues to be studied, but is also used for studying materials. One of the surprises is this is actually a very good materials tool for studying materials at very, very high or very extreme conditions before you reach fusion. So a little bit about superconductivity and pressure. In fact, these two areas were wedded at the very beginning by Camerlenionis. He carried out the first measurements of stress on elements, tin and indium. And now we have this periodic table. I'll be showing various periodic tables today. The periodic table of the superconducting elements. And now we know some 54 elements are superconductors or can be converted into superconductors under pressure, most of this done with diamond anvil cells. And some of you may be aware of the great excitement a number of years ago in studying the cuprate superconductors, which were the first high-temperature superconductors. This was announced with great fanfare at the Woodstock of Physics many years ago here at New York City. This was the highest TC superconductor measured under pressure, this mercury-bearing compound, and this, until the discovery of the hydrides, had the record for the highest TC, and I'll come back to this in a few moments. So what about hydrogen and its metallic character and its possible superconducting character? This really began with the paper that I mentioned earlier, the prediction by Wigner and Huntington that when you compress hydrogen, it must ultimately transform into some non-molecular atomic state. At the time, they suggested this would happen above 250 kilobars, 25 GPa. People sometimes say they predicted it at 25. It's actually, they were clever in saying it's going to be above 25 GPa. So they are right. It is above 25 GPa. And this was followed a number of years later by our colleague Neil Ashcroft, who said, okay, if we take this hypothetical state of this very simple metal, and you just apply the simple ideas of BCS superconductivity, it should be a very high temperature superconductor. It's got very high phonon frequencies because it has very light atoms. It has a high density of states, and it looks like it should have good electron-phonon coupling. So this really started the great excitement in trying to make metallic hydrogen. Vitaly Ginzburg had very similar ideas, who published about the same time. Now, much higher pressure, a lot of work has been done on the theoretical side looking for this, and this is a nice phase diagram to David Sepperly at Illinois, going out to much, much higher pressures and actually explicitly calculating what the superconducting temperatures would be, predicted these phases. So here are TC above 700 Kelvin, so this is clearly in the hot superconducting regime, but it's at very high pressures. But beyond this, and even more exciting, coming back to the work of Ashcroft and his colleagues, it's not just that a superconductor, it could have some very, very interesting properties because of the light mass, the one proton, or deuteron plus an electron gives you different spins, put them in a very high density state. You could have a superfluid that's metallic or a superfluid that's also superconducting. This would be an altogether new state of matter, but occurring at quite high pressures, above 400 gigapascals in their estimation, 4 megabars. But this is, really a new state of matter altogether, one that simply has not been seen in any other element, clearly at ambient conditions. So it also has driven the development of a lot of what we're studying. Well, those are very high pressures. We can reach those kinds of pressures in some careful experiments, but we really can't characterize the material that well. So there's been an effort to try to understand how we might be able to see some of these same phenomena, but at lower pressure conditions. And coming back to the work of Neil Ashcroft and his idea that you'd have superconductivity in metallic hydrogen, he suggested quite early on various ways to reduce that transition pressure. And he suggested going back to looking at basic molecular orbital theory, kind of along the lines of what I mentioned for Heitler, London, and Pauling, if we could simply take electrons from the bonding orbitals and put them in the antibonding orbitals in some fashion, we could destabilize this very strong molecular bond, and that might facilitate the formation of a monatomic solid with these, or liquid with these interesting properties. You could do this with photons, or you could do this by pressure ionization, somehow ionizing atoms that would then populate the antibonding orbitals of the hydrogen. And this was more systematically formulated in this paper, where he suggested there could be whole classes of hydrogen-dominant alloys that could exhibit these phenomena that would be like metallic hydrogen, some of these really interesting properties, but exist at lower pressures, maybe in the 100 GPa to 200 GPa range. Well, this drove a lot of the field, and when I started working in this high pressure field back in the 80s, this caught my interest. And during the 90s, we developed a number of techniques for studying various materials and elements, in particular under pressure as a starting point. We developed some techniques using this magnetic coil technique to study sulfur. We found that sulfur, common ordinary sulfur here, this yellow powder, can be turned into a superconductor. It's a pretty nice superconductor. It's got a TC of 17 Kelvin, not much compared to the hot superconductors I was describing, but at the time, this was the highest temperature superconductor of an element. About the same time, our colleagues in Japan were studying oxygen. So you think about 20% of the air, you separate the oxygen out, compress it, you can actually make it into a superconductor. A low TC, but a superconductor and a metal nonetheless. This is looking at a sample through a diamond anvil cell, seeing the metallic character of the oxygen. So this is pretty remarkable. These are remarkable transformations in other elements. So part of this effort that we were involved with involved just mixing different elements or molecules and doing various kinds of studies to look at what kinds of compounds would form at a range of pressure. In fact, during the 90s and later, we found that if we mixed hydrogen with various elements, kind of along the lines of what was proposed, you could make new materials. And we found a lot of really intriguing structures. We named these van der Waals compounds, but none of them were superconducting. Really interesting chemistry, though, and some of them were quite interesting also from the standpoint of hydrogen storage. And if you recall, 20 years ago, there was a great interest in developing new hydrogen storage materials for technology. And some of them have these really beautiful structures here. This is a structure of ice with some hydrogen in it. It has the same structure of quartz, SiO2. So really quite intriguing crystal chemistry. This is interesting over here because this is xenon bonding with hydrogen, two things you don't think about forming bonds, but it makes a beautiful structure. This one here was also interesting because it turns out to be the precursor of one of the high temperature superconductors that I'll come to. We simply didn't take it high enough in pressure at that time to see the superconductivity. So what changed the field really was not just searching this vast chemical space using chemical intuition or maybe our limited chemical intuition to find those phases, but actually the advent of structure search techniques. So coming back to this idea of an energy landscape and all the different ways you can combine the elements and the molecules and pressure and temperature, where can you look? With this new tool of that we can go up to megabar or many megabars of pressure, we have temperature. It's a vast space, thermodynamic space to explore. And this actually was an interesting problem in the 90s and the 80s, and it was dubbed the crystal structure problem, and maybe some of you remember this commentary by the editor of Nature, Maddox, who wrote, one of the continuing scandals in physical science is that it remains in general impossible to predict the structure of even the simplest crystalline solids from a knowledge of their chemical composition. Yet one would have thought that by now it should be possible to equip a sufficiently large computer with a sufficiently large program, type in the formula of a chemical, and obtain as output the atomic coordinates of the atoms in a unit cell. Well, it turns out you can do that to a certain extent now. So this challenge was met due to the efforts of a large number of groups over the intervening 10 or 15 years. And this was done by marrying various genetic algorithm approaches using what Maddox said, very large computers and clever algorithms for exploring space to look for crystal structures. And here's an example of just one. This is due to Eva Zurich at Buffalo, the X-to-lot method. So you take these combinations of elements or atoms, and you can then shear them, make them ripple. You look for energy minima. You can then feed this into some kind of global picture here on this energy landscape and look for the lowest energy structures. And you have to marry with this, well, of course, with a model for the electronic structure or the total energy of the system. And by this time, density functional theory was working pretty well for some of these elements of interest for that part of the periodic table. So it was really quite successful. So these genetic algorithm approaches really led to the discovery of a lot of different materials, not just high-pressure materials and not just the kinds of materials I'm talking about, but really it has been revolutionary. But it was particularly important for guiding us as experimentalists principally in looking for new superconductors. In fact, within a few years, a large number of beautiful structures were emerging from these calculations, and some of them really are quite hydrogen-rich. In a way, these aren't new structures. Some of them are known structures in completely different materials, like this being a zeolite. It's a structure of a catalyst, but it has hydrogens instead of silicon and aluminum. So these are really intriguing structures from the standpoint of hydrogen, very hydrogen-rich. And in fact, the ones here in red were, over the years, discovered and confirmed. And basically, the structures were confirmed, and pretty much the TCs using the conventional theory of superconductivity. I just want to give you an example of the two first ones, and that is the case of H3S, or hydrogen sulfide. This is the work of my colleague, Mikhail Emergent, who died a couple of years ago, a close colleague of mine. He took this theoretical calculation, immediately went to work and looked for this structure and superconductivity, and indeed found it, measured the isotope effect, which matched the conventional theory. We, on the other hand, decided to look at rare earth-bearing materials and the higher hydrides, and we did our own calculations and found this particular structure, lanthanum H10, mapped out the structure by X-ray diffraction, and then within a few months actually did an experiment where we could measure the superconductivity. This was actually a much more challenging experiment because we had to make the sample by laser heating the sample inside a diamond anvil cell without chemical reactions affecting the electrodes. So it was a real challenging experiment, but it was a benchmark for us and for the field. Also, an important point is that it took a number of years for any other group to reproduce the H3S results because it was a tough experiment. However, for this one, it was reproduced within a few months by my colleagues in Mainz, but also by now some 6 or 8 different groups. So this has all been reproducible science, and it's been, I think, a great success. So now I want to point out that a large number of binary hydrides have been studied, and here's another periodic table. This is now the periodic table of the binary hydrides. Those in yellow are those that have been calculated first and then confirmed experimentally. The agreement is quite good. And the rest really are pretty well described. So we don't have experiments for all of them, but we have a pretty complete understanding of this system, at least up to, say, 300 gigapascals, which is the range of pressures where we can do these measurements. So it's pretty much a solved story, and again, I think it's a great success. So now we have this picture of TC versus year. Here we have the original discovery of Camerlingionus in 1911, the conventional superconductors, the slow growth in TCs as more and more materials were being discovered, the bump up in the cuprate revolution, the peptides here, and then now we have this hydride regime here. This is summarized in a beautiful paper by Warren Pickett. And he also made an important point that I'll come back to at the end, and that is in all of these cases, and this goes back to some of the earlier ideas about superconductivity, the maximum use in the superconductivity is always close to some kind of structural and electronic instability, which is a challenge actually for theory. And there are also, in these calculations, really metallic hydrogen-like materials. It's kind of like doped metallic hydrogen. But there are interesting questions now. Can we get to higher TCs? In fact, is there a limit on the superconducting temperature? And also the very important technological question, these are stable only at very high pressure. You cannot recover them to ambient or near ambient. Is there lower pressure stability? Can we learn something about these by changing the chemistry or somehow the synthesis conditions so that we can have low pressure, at least kinetic stability for these materials? So this leads to broadening our chemical space and at first adding another element. So now we have ternaries, not just binaries. And here I want to point out the words of Bernd Matthias, who was one of the most important persons in the field of superconductivity, a hardcore experimentalist, but he had a great disdain for high temperature superconductivity. He wrote, "Room temperature superconductivity, regardless of 1,000 statements by theorists and an equal number of theories, is, in my opinion, pure science fiction." But he wrote, a few years later, just before he died, the field of ternary superconductors is still comparatively new, and there is still some hope. Now, he wasn't talking about hydrides at that point, because the hydride superconductivity was not yet developed, but those were interesting words of wisdom. And now we see a new era where we're looking at least theoretically, much higher temperature superconductors. This is an important prediction by my colleagues at Jilin University in Changchun, China, and they, back in 2019, predicted this combination of lithium, magnesium, and hydrogen could have this astonishing hot superconducting temperature of 470 Kelvin. So obviously an important one to make. It's actually metastable under those conditions, but it's an important one, and we're still chasing it to a certain degree. Here's another study that I happen to be involved with. If you just add some scandium to lanthanum and look for the lowest energy structures, you find some pretty interesting phases, this one with a TC above room temperature as well. And so this continues. This is the work, again, of Eva Zurich in a paper that just went online a couple of weeks ago, and she's examined with her students a broad range of different classes of ternaries now. So we have a very wide space. It really taxes the structure search approaches because of just one extra element, but then all the different structures and all the different pressures and temperatures you have to look for. So she's mapping out the different structures that are possible. Some of them are fairly high, but some of them are fairly low. But this is important for feeding into machine learning calculations, for example, to speed this up, something I'll come back to in the end. So what I want to do is just give you an example of two ternaries that we've looked at. One that's pretty well established. This is work that was just completed. In fact, the paper was accepted in Nature Communications today, I believe. And that is that the simple ternary of, okay, let's just mix yttrium with lanthanum. What new phases might we find? And this was done, this experiment was done with the new upgraded advanced photon source, which is a marvelous resource for this country and the world. It was down for basically 2 years, and its accelerator improved so that it's already very bright beam, which was in this fan, is collapsed into a spot here. So we have several orders of magnitude higher brightness, which is very important for our small samples. So this is now a very important facility. They call it the world's most powerful X-ray microscope, and I believe that's a fairly accurate statement. So we can use this X-ray microscope to probe in great detail these phases that we make, because some of them have inhomogeneities and differences that we need to explore. So if we combine that with various ways we're putting electrical leads on our diamonds for electrical measurements, and then we take this to the advanced photon source, which is just 30 minutes away from my lab, and we use these micron-sized beams, we can map out in great detail the sample. So this is a sample sitting at something like 1.5 to 1.8 million atmospheres pressure. We're sending the X-rays through. At the same time, we can measure the electrical resistance. We can map out where the leads are. And this is an interesting case because we see from our electrical measurements, there are two superconducting transitions. And we know from the diffraction, one is due to a hexagonal phase and one is due to a cubic phase. And so we have this beautiful map now, which allows us, in this sort of complicated slide, don't look at all the details, but the point is that we can map out by the portions of the sample that are due to one phase versus another, so we can effectively spatially resolve the resistance in this measurement. And so this ability to spatially resolve what's happening in these high pressure cells is very important also for looking at the Meissner effect, where one can use NV centers, which are little magnetic probes in the diamond. This is something we did years ago, and that's now been implemented in very nice experiments being carried out at Harvard by Norman Yao's group, where they could do Meissner effect imaging of these samples also under these same conditions. And then the goal is to combine this also with the X-ray diffraction. So the second ternary I want to tell you about is one that's been controversial, and that is the work on lutetium, nitrogen, and hydrogen. And this was work by colleagues at Rochester. They announced in March of 23 that they had found evidence for some kind of superconductivity at approaching room temperature, really in the vicinity of room temperature, but now at 2 orders of magnitude lower pressure, pretty close to ambient, 1 GPa or 10 kilobars. Unfortunately, this paper was retracted for a number of reasons that I don't want to get into, but we were still quite interested in whether or not there's something to this phenomenon. So we started to work on this problem. Here's a picture of the model structure. So here we're moving from lanthanum on one end of the rare earth row all the way over to lutetium, where we have all the F electrons filled, and really the question is whether that somehow is affecting the difference in the superconductivity behavior of the hydride of lanthanum versus the hydride of lutetium. So we did our own measurements. We got samples from Rochester and also samples from our own lab. In fact, what we found is in most cases there's no superconductivity, but in a few you can see these resistance drops, and this is a function of pressure. This is the data that was shown in the previous slide. These are our data. Our resistance drops are larger because we have a larger sample, but we actually reproduce, at least in this one sample, what was reported in this paper. We've also done magnetic susceptibility measurements, very similar to what we did for sulfur years ago, and studied a lot of other materials and see quite similar behavior. So if we plot all of this data together, we see a very similar picture of the variation in superconducting temperature, or at least some kind of critical temperature, versus pressure, now again, at quite low pressure. And this was quite exciting, and actually my students were very pleased because when we reported this online on the archive, a story appeared on the front page of the Times. So this was very nice for the CVs of my students who worked on this. Now we're still working on it because it's very hard to reproduce these results. Most of the experiments fail. They fail for 2 reasons. The samples are mixed phase, and also there's a time dependence You can't keep them in the superconducting state very long. But the question arises, has this been reproduced in other labs? And what I've learned in the last 6 months or so, in fact, a group in China has seen something quite similar. Here's a similar kind of sample, and they see a resistance change at about 240 Kelvin, really quite close to what we found. But there is this time dependence. After several cyclings, this goes away. So something intriguing is happening, but we don't fully understand. Another group has done something quite similar, and they've also applied a magnetic field, and they see the kind of broadening you would expect in a magnetic measurement. So this is supporting evidence for something happening in this system. Again, here are data for comparison. So we'd like to understand this theoretically, and I gave this project to a very talented student to see if he could come up with some way in which we might understand this. These are very different materials than the superhydrides I talked about before, where you might have 10 hydrogens per metal. Here you have 2 to 3, depending on the stoichiometry. So is something different happening here? Well, what he did is he decided not to use a structure search method because he wanted to look for all the different possibilities you might have in terms of the electronic properties, not looking for the energy necessarily, looking for metastable phases, in fact, because the structure search approaches were not finding anything interesting. So he built basically computers, crystal structures on a computer, sort of the old-fashioned way, and was able to find various combinations of layered structures that had really, really remarkable electronic properties. This is somewhat technical, but what he found was certain layerings and certain compositions produce extremely flat bands right there at the top of the conduction band, and this gives rise to a very sharp peak here, which is also known as a Van Hove singularity, and it's a harbinger of superconductivity. We can't calculate the superconductivity because of the size of this unit cell, but it's a smoking gun for something interesting happening electronically. And what's also interesting is this is much, much sharper than what we have in these other materials, which we know are superconductors. This is very, very sharp in comparison to what we have with lanthanum hydride, yttrium hydride, and hydrogen sulfide. So if it's not superconductivity, it's still an extremely interesting electronic material. If you look in real space, which is something more appealing to chemists, is here we have a picture of the what's called the integrated local density of states. And what you find here are, these are the hydrogens, and so you have embedded inside this structure, even though it has fewer hydrogens, it has sort of like an embedded lattice structure of hydrogen. So it does have a metallic hydrogen lattice or cage structure, and if you can use systematics to estimate the TC, so that's consistent. Here is the Brillouin zone, so for those of you who are interested in topological materials, it has flat bands and Dirac cones and so on. So it's really quite an intriguing material apart from its potential room temperature superconductivity. The student also, before he graduated this past summer, decided to go one step further and ask, could we see the same kind of phenomena in other materials, replace the lutetium with other elements? Could you see some of these same intriguing effects? So he went to work, again, using, in a sense, chemical intuition, not doing anything more sophisticated than that, just looking at electronegativities and electropositivities of atoms, and he came up with a scheme where the core unit that looks like it's responsible for the intriguing properties is this RH11 unit, and so if you substitute elements in different ways, you can see the preservation of not only the stability, but also the electronic properties. And the more atoms or different elements you include, the more versatility you get and the more stability and interesting properties. So we came up with this picture of a 6-component hydride system that potentially could be a room temperature superconductor that's stable at ambient conditions. The trouble is we don't have an accurate estimation from this sort of heuristic approach of just where to look and how to make it. So the definitive predictions of the structure, the composition, and the synthesis, and the TC really are beyond current computational methods. It's something we can't do with the conventional computational search methods. The space is too large. We're going to have to rely on a lot of machine learning of the features to really make predictions here. So this is a grand challenge for computation. I'd like to comment very briefly on other challenges to theory before I finish. And one comes from what I mentioned earlier, the problem of the very large zero-point motion, the quantum character of hydrogen. Most of our calculations, going back in physics and chemistry for many, many years, just freezes the system and uses the Born-Oppenheimer approximation, and you treat it as classically. You really can't do that, especially in these high-pressure regimes. And this is something we noticed when we did our first calculations on lanthanum H10. We did what's known as path integral molecular dynamics, where we tried to take into account this quantum character. These beads here are the trajectories of the particles during a simulation. And what you find is even at room temperature, and this is in the vicinity of TC, there's a lot of quantum character. And if you increase the temperature, you in fact see what looks like sublattice melting. So you have this curious situation where in the vicinity of superconductivity, you also may have a fluid state or a near fluid state of the hydrogen. This is not what goes into actually the theory of superconductivity. So there's a real problem. This is also a simulation of the classical molecular dynamics. I guess I can skip that anyway. The second problem, and I'd say as a challenge to theory, has to do with the problem of being near instabilities, and that also is connected to this very large zero-point motion effect. This is a complicated diagram, but basically it shows the vibrational frequencies of the system, and also these are bands that show how much a particular vibration is coupled to the electronic subsystem, so the electron-phonon coupling. And what we find in all of these systems when we do these calculations, and this again was for lanthanum H10, is that you get the maximum superconducting temperature as these modes soften. They're very close to zero. When they're close to zero, you're in an anharmonic regime. In some cases, it may be not bound. It may be diffusive. But in order to do the calculation, we have to use the harmonic approximation, which is clearly problematic. So just in the region where we want to get an accurate prediction of what TC is, we really don't have the tools necessary to do that. So this is another challenge for theory. So all the action really is right here, where the hydrogens are very, very close to having basically a zero bound state. They're not in a harmonic well. So in the last couple of minutes, I just want to touch on two other systems, not hydrides, but work that we're doing, and it touches on the work on hydrides. And coming back to cuprates, and this question of how high in temperature can we get the cuprate superconductors using these same high pressure techniques. This is a compendium of TC versus pressure for all these different cuprates. Many of them were presented at the Woodstock of Physics or in the years that followed. Some go up and down. Some have some very interesting non-monotonic shapes. This is the mercury-bearing copper cuprate here that has the highest TC. So my student, another student just before graduating, decided to try to study one of these. So he looked at this particular material, which is this bismuth strontium calcium cuprate, or BISCO, this one with this 2-2-2-3 structure, as it's called, and pressurized it. And in work he just completed, he showed, in fact, at low pressure, there's this non-monotonic behavior, but then it takes off, it keeps going. The experiments are now here. He actually is doing measurements as we speak at Argonne to try to get this further, but this is already close to 200 Kelvin. So this is the highest TC measurement of a cuprate, which is quite exciting. And in fact, this idea that maybe you could get cuprates to room temperature was something that was discussed at the Woodstock of Physics, which was presided over by Neil Ashcroft, and I believe he made that statement back at that meeting. I happened to be there. I was a postdoc at the time. Is this, for the people in the field, is this evidence for a different superconducting dome in the system? And will TC reach room temperature at higher pressures? We simply don't know. So still exciting work on the cuprates. There's now a lot of interest in the nicolates if you're in the field, but the cuprates under pressure are still pretty exciting. Finally, I want to discuss another example of some recent work coming back to our friend sulfur, work that we did back in the 1990s, the discovery of superconductivity here. And one of my postdocs did an experiment and asked the question, what would happen if we went to extreme magnetic fields while in the superconducting state? What might we see? What he found was, now this is resistance as a function of magnetic field. He found this huge peak here that comes in when you're in the superconducting state. And that led him to create this phase diagram, which is a new kind of phase diagram. It's temperature versus magnetic field. Here's the metallic state, and here's the resistance state. But in this intermediate regime, we believe this is something in between the two. So it's a bosonic state where you have bosons, Cooper pairs, but they're not coherent. So it's not superconductivity because the bosons aren't coherent. This kind of thing has been seen or proposed in disordered materials and thin films, and we believe this is the first example of this interesting state of matter in a bulk material, because this is a bulk, very simple material, simply sulfur. And again, maybe one more example, going to still higher pressure, more emergent phenomena, not necessarily superconductivity. I mentioned the electrides and the scrambling of electrons that occur in sodium. We take other elements, for example, simple aluminum foil, and we compress it maybe up to 100 megabars. We too will expect to find these very, very interesting structures that really are reminiscent of a type of chemistry occurring at extraordinarily high pressures. This is far beyond what we can do with a diamond anvil cell. We have to use dynamic compression techniques like those at a National Ignition Facility, but this is a regime that's ripe for the study of new topological materials and other states of order, of correlations in electronic order that might ultimately be useful. So to conclude, we have now this picture of the increase in TC, superconducting TC with year, going beyond Kamerlingh-Onnes's discovery. We have the regime of the conventional superconductors, the cuprates and the pnictides, and now we're in the regime of hydrides and even some of these cuprates, all made possible by high pressure techniques. Will we ever get to utilizing or deploying these in technologies? I think it's only a matter of time. It may be a decade, maybe 2 decades, but we're confident that these discoveries will have technological implications as we develop ways to stabilize and produce these materials for various applications. And then finally, I'd like to point out this very nice review came out in January commenting on the state of the field, and I like it because none of the authors are in the field of hydride superconductivity, and none of the authors are high pressure folks, but they concluded in this very thorough study that hydride superconductivity is here to stay. So we believe the future is bright for continued discoveries in these and related materials with close synergy of experiment, theory, and computation. I think there's a great role for the Simons Foundation in helping this along further to go after some of these other phenomena that I have been describing so far. So with that, thank you very much.